All right, so let's look at this problem. So you can see we want to determine the maximum moment at B. B just happens to be right here in the middle. So remember on these influence line problems, you're going to be specified a location and then what you're looking for, reaction, shear force, bending moment. In this case, we're looking for moment at B. Okay? And then we've got this moving load scenario here, some kind of truck maybe. It's got a 2-kip load, 5-kip load, 12 feet apart. So they're going to move from the right side, they're going to cross the structure, moving right to left. So what's the first thing we have to do? We need an influence line for the moment at B. So I'm going to use my Mueller-Breslau idea. And quickly I can come up with the qualitative view of this. So I'll go ahead and make some marks to kind of keep it orderly. There's the end of the beam. There's the middle of the beam. Now remember what we do in Mueller-Breslau is we'll come here and we'll imagine a hinge, right? That releases the moment. And then we'll come back and we'll apply positive bending moments to both sides. And then you have to imagine how that structure would deform. And the way I like to think about it is you look at point B, is it going to move up or is it going to move down? It's going to move up. So you're going to end up with a qualitative influence line for moment that looks something like this. And I'll go ahead and just bring these dimensions down. So there's the qualitative shape. To quantify it, I just need to find the value right there. So that means my moving unit load, moving across the structure, if I stop it right here, that will give me that value. So what I'm really looking at is a structure that looks like this. I want my unit load right in the middle. And again, why did I pick that point? Because that point corresponds to this point on the graph, and that's the ordinate value I'm looking for. So at that position, I have a reaction at A and a reaction at C. And then I'm going to come back, since this is the moment at D. Oh, I wrote D, didn't I? That's B, isn't it? Sorry about that. Let me make that into a B. A poor B, but a B nonetheless. Okay, so I'm going to come back and I'm going to cut the structure here. And that way I can find the internal moment at B. Do you want to work the left side or the right side of the structure to find that? Want to work the left side? Okay, so that means I need AY. So let's find AY first. So I will sum moments about C. Make sure it's in equilibrium using right-hand rule. And about C, my unit load creates positive moment with a moment arm of 100. And AY creates negative moment about C with a moment arm of 200. So it looks like AY is 1/2. That should not be surprising. With a load of 1 right in the middle of a simply supported beam, you'd expect the reactions to be half and half, and that's what we got. So now I'll cut my structure. You guys want to work the left side, so we will. We'll cut it at 100 feet, 100. I just saw from my reaction AY, it's 1/2. And really, you can have the 1 on there or not. It won't really matter because it's going to be right at the cut. It won't create any moment. So you can or cannot include it. But I do want to know the moment at B. So how do I find this internal moment? Well, some moments at the cut. Done that a few times. So, using right-hand rule, the internal moment is positive, and the reaction moment is negative. 1/2 times the moment arm of 100, so it looks like the moment at B is 50 feet. Now remember, the moment there is no dimension for the force part, so that's why there's no unit on the force reaction AY, and that's why the unit for the moment is only feet, not kip feet. So remember, this will have the units of just feet, and this one now is 50. And I have my influence line. That's kind of like half the problem. So now what do? Well, we're going to let this set of moving loads move from the right side to the left side across the structure. And we want to give each one of our loads, so there's two, so there'll be two cases. We want to give each one an opportunity to be at the maximum height, or the maximum value, which happens to be right in the middle. So let's start there. I'll call that case 1. And give me just a second to redraw the influence line. So there it is. And don't forget, this has a value of 50. And that's going to be also have the units of feet. So I'm going to let my first load come over, which in this case is 2 kips. So I'm going to let the 2 kip hit right here at the top. And then 12 feet back is the 5 kip load. See, I've let my truck drive on, and I've let it come all the way till the 2 kip is at the maximum value of the ordinate, which just happens to be right in the middle. You can see I'm going to need the ordinate value right under the 5 kip. So how am I going to find that value right there? You can do a couple different ways. You can do similar. Yes?
So you're going to just treat it as you have 2 cases, loads on at the peak. What would happen if it was centered over that location?
Well, if it was centered over that location, the 2 would have a smaller value, and the 5 would have a bigger value. All right, that'd be somewhere in between the max, which is letting each one get a chance to be the max. You can probably see this is not going to be the controlling one. Probably the controlling one is when the bigger load, the 5 kips, hits the top of the hill. But you got to check every case if you're not sure.
But couldn't there be more than just 2 cases
to
achieve peak?
No. These are the 2 limiting cases.
Okay, and that's always going to be the case.
You're going to have, right, you're going to let each one of the forces, if I had 12 loads in my setup, I would have to do 12 cases. I'd have to let each one go to the highest ordinate value of the thing I'm looking for. So if this is 50, what's this value right here? Well, there's a couple different ways you can do it. I always like to do the slope. So what is the slope of that line? It's the rise, which is 50, over the run, which is 100, which ends up being 1/2. So every foot I move to the right, I drop 1/2. I'm moving 12 feet, so that should be 6. 50 minus 6 is 44. So now I can compute my moment at B. It'll be 2 kips times 50 feet plus 5 kips times 44 feet. So this is 100. This is 220. 320? Somebody check me on that. I got 320. You guys got 322? So that'll be kip feet. So that's the moment at B for this position, with the front load, the 2 kip load being right at B. So the other possibility would be very similar. Except now, we're going to let the second load, the 5 kip load, be at the top of the hill. And that means 12 feet forward, the 2 kip load will be there. What's that value? Well, in this particular problem, you can see the slope on the left side and the slope on the right side are the same, right? So I still got a slope of a half. If I move 12 feet, that means I'm going to drop 6. So this is still going to be 44. So the top is 50, and this bottom will be 44. So I think I can squeeze it in right here. So the moment at B will be 2 kips times 44 feet plus 5 kips times 50 feet. And that's 88 plus 250, that's 338? So you look at those two values, which one is the biggest one? 338. So the moment at B would be 338 kip feet. So just a little recap. For every force in your sequence, you'll have a case. And the objective is to let each force in turn go to the point on the influence line that creates the maximum influence. In this case, it's moment at B. And you see in this diagram, it's pretty simple. There's only one spot. We have seen some influence lines where there might be a large negative value and a large positive value. So you'd have to look at possibly both cases in that scenario for homework. On the exam, I wouldn't let you sit there 25 minutes trying to check every case. So I'll probably narrow it down and ask you just to look at a positive moment or a negative moment. In this case, I didn't have to specify because it's all positive.
If it's obvious which one's going to be the main load, do we have to show all our work?
It's that word obvious.
Okay.
What's obvious to you and what's correct may not correlate well. So I would encourage, no, you're right. If you see it, hey, this is the only one I have to check, and it's right, you're golden. But if you see what's obvious and it's not correct, then you have not solved the problem. So I would, even in your head, if you don't have to go into this much detail, you might be able to, in your head, just write down these two lines. You may not need to do this. I'm doing this kind of instructively to help you see it. You don't have to duplicate the solution this way. You might just be able to see it in your head. Oh, yeah, 2 here and 44 back there, da-da-da, boom. And you could just, it could, literally, on your result, you would have that in 2 lines, possibly, which is okay. But I would encourage you, if you're unsure, to at least show me what you're thinking so I can kind of see where you made your mistake. Because sometimes these simple things like finding the value of the ordinate on this line, students find that to be challenging for some reason. It's interesting how much of being successful in engineering school goes back to algebra from the 9th grade. So you have your algebra teacher to thank or to curse, whichever you would prefer. I had a pretty good algebra teacher, so I was okay. Any more questions? That took us whopping 11 minutes to do.
It's a long time.
It's a long time.